Good morning, everyone. Thank you so much for joining our webinar today. My name is David Kallenbach, Head of Technical Solutions and Support at Framos, and I'm thrilled to be your host for this session. At Framos, we are dedicated to making latest imaging technology easily understandable and accessible. With that, we are supporting our clients to excel in building innovative imaging solutions of tomorrow. Founded in 1981, our company has a rich history in the classic distribution business with a clear focus on image sensors. Over the years, we've expanded our services to cover the entire customer journey. The frame of support ranges all the way from technical consultancy, requirements engineering, and product selection support over efficient distribution, bring-up support, and troubleshooting. Additionally, Framos provides a robust ecosystem that includes reference drivers, supporting IP cores, connectivity, and off-the-shelf hardware solutions, as well as custom solutions tailored to our client-specific needs. For today, I'm excited to have our long-standing partner Sony joining us to share some insights on the latest image sensor releases and advances in industrial 3D. Particularly, we are going to learn more about state-of-the-art time-of-flight and event-based vision sensors and how they can be leveraged in industrial applications that benefit from 3D vision. Let me kindly introduce you to our two speakers for today. Our main speaker will be Tom Jellicoe, who leads the growth and business development team at Sony Semicon Europe. He leverages over a decade of experience in developing and launching innovative technologies. And our second speaker, Flavien Irigoyen, technical imaging expert at Framos. He adds another 20 years of experience around CMOS image sensors to the round and was involved with direct and indirect time-of-flight pixel developments, as well as event-based image sensors and camera development. I'm looking forward to both of them providing their expert perspective in today's discussion. Here's a quick look at our agenda for the webinar. Right after my short introduction session, I'll hand the mic over to Tom, who will speak for about 15 minutes about challenges and advances in ToF and Event Vision, as well as real-world use case examples in robotics and warehouse automation. In particular, and besides others, Tom will explain how Sony's latest direct time-of-flight sensor IMX560 supports cost down for LiDAR systems. Tom will then hand the mic over to Flavien, who is going to explain how Framos supports enabling customers to create imaging solutions around the mentioned image sensors. After about 25 minutes in, we'll wrap things up with a 5-minute Q&A session where we'll address your questions and provide additional insights. Before we dive in, I'd like to highlight the question feature in this webinar platform. Please use this icon to raise questions during the webinar. Questions will be tackled during the Q&A session. For any unanswered ones, we'll come back to you soon after the webinar. Now, without further ado, let me hand it over to Tom from Sony to kick things off.
Thank you very much, David. Thank you for the introduction. So as you heard, I'm Tom. I lead the growth and business development team at Sony Semiconductor in Europe. So our team managed the launch of new sensor categories, new technologies, and new applications based on Sony products. Today, I'm going to cover, as you've heard, I'll cover two topics. Both are, let's say, relatively fresh new technologies from Sony Semiconductor relating specifically to industrial 3D imaging. So the first of those is our new SPAD-based direct time-of-flight image sensor IMX560. I appreciate there's a lot of jargon in that introduction, but hopefully that will become clearer later in the presentation. Can we go to the next slide, please? Thank you. So making a distance measurement by time of flight is a relatively simple principle to understand. The speed of light is basically constant, so we can time how long it takes light to leave a camera, hit an object, and then come back. And then from that, we can calculate the distance. In this plot, we're showing the typical operating ranges for our two classes of time of flight imaging products. So I guess many of you will already be familiar with our indirect time of flight products, which have been in the market for a few years now. Indirect refers to the way we calculate the time of flight. So rather than directly measuring it, so sending the light, starting a timer, and timing how long it takes to get back. Instead, we calculate it from a phase difference between sent light and received light, which is modulated. This is a relatively simple measurement to perform on the chip, so we can do it with many pixels, which allows higher resolutions. But the modulation and illumination put some constraints on the range. So typically these cameras are limited to less than 10 meters or so. With our new sensor, we directly time how long the light takes to reach a target and return. So the modulation distance constraint is removed. So this class of sensor are typically used in LiDARs that you might see in the market now. And in principle, our sensor can measure up to a few hundred meters. Although we anticipate that this won't really be necessary for most industrial scenarios. But we do expect that our new longer range direct time of flight product will complement our existing iToF products and open up some new applications. Can we move to the next slide, please? So this is an introduction to some of the key features of IMX560. So like most of our recent products, it's a stacked chip, and it consists of a pixel array on top of a logic chip, and this is fabricated using our copper-copper connection process. It's pretty high resolution for a direct time of flight image sensor, so you can really do true 3D imaging. It's not just a point-by-point measurement. Quite a unique feature of this product is the ability to measure both the primary detection peak and multiple echo peaks. So what we can do with IMX560 is really calculate the distance of objects on the chip and output it directly from the chip. We also have some additional features on the chip to help with calibration, and it's got a MIPI interface for simple integration. So if we go to the next slide, we can delve into a little bit more of the detail of the sensor characteristics. So IMX560 has about 10 micron single photon avalanche diode, or SPAD pixels. These are incredibly sensitive, so they can be single photon sensitive. And the reason for this is to facilitate long range measurement and very high photon detection efficiency. In terms of the resolution of the sensor, this IMX560 has about 100,000 SPAD pixels, but the nature of SPAD pixels and how they're used for distance measurement mean they need to be binned, so you need multiple pixels to make a distance measurement. And in IMX560, the minimum binning arrangement is 3x3. So this allows about 10K distance measurements per frame, or kind of 10,000 usable DTOF pixels. The substrate is silicon, so this means it can work with silicon compatible emitters, edge emitters, or VCSEL lasers. The product has on-chip time-to-digital converters, which can sample at up to 1 gigahertz, and it supports two different types of readout mode, line mode and array mode, and I'll explain the purpose of those on the next slide. So the purpose of having multiple readout modes is to allow IMX560 to be used in multiple different LiDAR architectures. So in line mode, which is the image on the left, the image sensor is effectively turned on its end and then scanned around the scene. So it's kind of used like a linear DTOF sensor in this mode, but it will be binned as well. Because of the aspect ratio of the sensor, this allows us to have up to 192 vertical macro pixels, so it can create very dense point clouds in this scanning mode. In the center image, we show array mode. So in array mode, the sensor is orthogonal to how we use it in line mode, and you can think of it a little bit like a rolling shutter CMOS image sensor, in that we read line by line. So when we pair this with a line addressable laser, such as an addressable VCSEL, we can emit and measure line by line and build up full 3D point cloud frames, but in a solid state mode. So this is really valuable for applications in challenging environments, such as high temperature variation or high vibration environments where mechanical systems can be a bit challenging to calibrate and for longevity. So the sensor readout, as I mentioned before, is really analogous to a rolling shutter image sensor. So we can't do a sort of a global shutter measurement where we measure all lines simultaneously. So we can't do a flash type measurement, but we're confident that between the line mode architectures and the array mode architectures that we can cover the majority of industrial use cases. So that's the end of my brief introduction to IMX560. Now we'll move on to something quite different. So if we can move to the next slide, please. So the next section, rather than being a new product from Sony, it's really showing you some work from one of our development teams, which we hope will inspire customers to use our existing event-based vision products in a new application, essentially. So I assume that most of the people on the webinar will be familiar with event-based vision, but in case some of you have somehow evaded the marketing efforts of Sony, Framos, and Prophecy over the last few years, I can cover a quick introduction to event-based vision, or EVS. So the sensor works fundamentally differently to conventional frame-based CMOS image sensors. The pixels only register changes in light intensity, and it registers these as an event. So only the elements of an image which change are recorded by the sensor, but with much higher time resolution and lower latency than a conventional CMOS image sensor. The examples used on the left here to illustrate this are imaging a rotating red ball with both a frame-based camera and an event-based vision camera. So on the left, you can see in each frame we get kind of a snapshot in time of this red ball with substantial motion blur, and then a lot of dark pixels around it where there's no information. So we actually get sort of relatively little information about the ball's movement through 5 frames. In the center, we show how it would look imaged with an event-based vision sensor. And in this case, we have very low latency and we only measure the changes due to the movement of the ball. So you can see we can track it with very good time resolution. If we go to the next slide. So because of the way that the EVS works, this results in 3 key benefits for 3D measurement by either laser triangulation or by structured light. So the first is high speed, so low latency and high temporal resolution. Because the events are read almost as they appear, rather than waiting for the frame to complete, the latency between measurement and readout can be much quicker than in frame-based approaches, so we get this much better time resolution. The next benefit is sparse data. So only the events are read out. So the downstream processor doesn't have to process all the many pixels where nothing has changed and no information is present. And the final key benefit is high dynamic range. So as each pixel is read out independently, we don't have the issue of trying to get dark and light objects properly exposed in a single frame. So we can really use the full logarithmic response of the pixel to measure each event asynchronously. So we can use that full high dynamic range. I mentioned that this has benefits for laser triangulation and structured light. For the rest of the webinar, I'll focus on laser triangulation, but for anyone with a specific interest in EVS structured light measurement, there's an evaluation kit available from our partners Prophecy. So please, if you're interested in that, get in touch with our friends at Framos who can facilitate that. Can we go to the next slide, please? So how does a laser triangulation measurement work? So I've tried to show here with these images. A laser line is projected onto the object that we'd like to measure. An image is taken of that laser line on the object, and then the laser profile is extracted from the image. If the object were completely flat, the line would look straight. But if there's any sort of 3D structure to it, then there'll be deviations of this straight line, and we can use the deviations of the line to calculate what the 3D surface is. So here, the example we're using is a rectangular block. And the reason it's called triangulation is you can imagine you can form basically a triangle between your camera emitter and laser lines, and then you can use basic trigonometry to calculate differences in depth. For many laser triangulation cameras as they exist today, which use frame-based image sensors, the laser line is often static with respect to the camera, and then objects are measured either by scanning the camera over the object or scanning the object past the camera using a conveyor, for instance. In our EVS R&D system, we've done things slightly differently. Instead of having a static laser with respect to the camera, we actually scan the laser line back and forth over the objects we're measuring using an oscillating mirror, but at a fixed distance from the camera. But it's also possible to measure in the same way as a conventional frame-based laser triangulation camera. Can we go to the next slide, please? So to highlight why there are some potential benefits to using EVS for laser triangulation, I've tried to put a sort of side-by-side comparison with conventional frame-based approaches. So when we do laser triangulation with a frame-based sensor, each frame acquired only really gives you depth information from the pixels where there's laser light. So you could argue that this is kind of a 2D or a 2.5D technique. And then you have to acquire many camera frames in order to assemble a full point cloud or depth map. So often this requires specialist image sensors with extremely fast readout at sort of tens of thousands of frames per second to measure enough lines to build up a full 3D point cloud or depth map. So for example, if you need 1,000 lines to measure your surface and you're operating at 20 kilohertz, that's still only about 20 point clouds per second. And it's a lot of frames per second to process, which adds cost and complexity. So event-based vision elegantly avoids some of these issues. You're no longer limited by the frame rate, instead just by the movement of the laser generating events. So you don't need to perform this feature extraction step on every frame because the event-based vision sensor has already done this for us by the fundamental operation of the sensor, because it only sends us events where the laser is, and it kind of ignores all the pixels which don't have any information. So by working this way, we can effectively directly and continuously generate 3D surfaces by using the timestamps of the events to calculate where the laser was when that measurement was made. So the purpose of this comparison is really to highlight the sort of innovation in using event-based vision, but please don't construe this as a suggestion that EVS is going to replace all frame-based laser triangulation cameras, because it won't. There are pros and cons to each. The accuracy and precision of EVS are limited by the resolution of the image sensor and the jitter in the pixel readout. So it's not as accurate or precise as traditional laser triangulation cameras can be. But please see this as kind of a new category of 3D measurement for when high speed and reasonable precision are required. So, you can imagine it being mounted directly on a robotic arm to control the robot, or for measuring items on very fast moving conveyors or moving at variable velocities. Sorry, I've had to go through that operating principle quite quickly, but hopefully it's kind of vaguely understood. I can now show you what this looks like in practice. So if we go to the next slide, I've got some data captured from one of our test systems in the lab. So we decided to set ourselves quite a big challenge, see if we could image an operating fan in 3D. So the fan moves at about 1600 RPM, so it's about 27 rotations of the fan blades per second. So this is a very challenging object to measure with a 3D camera. Because with our EVS 3D, we can generate point clouds at over 200 frames per second. It means that we can have multiple point clouds per rotation with minimal motion blur. I mean, I'm not sure how well this is rendering on your screen. On my screen, I can see clearly that the edges are captured well. There's minimal motion blur. You can see the various positions of the fan as it rotates round, which is very challenging to do with other 3D techniques. Can we move to the next slide, please? So the next slide is about success stories. Hopefully you'll forgive me for being maybe a bit forward-looking here. As these are very new technologies, the successes will come later. So I think here my intention is to inspire your future successes rather than being able to report on the successes we've had already. But let's start with IMX 560. So the biggest benefit this offers to customers is that IMX 560 provides so much of the LiDAR system in a single package. So it's not just the detector, but there's significant signal processing and system control in the logic layer. The sensor doesn't just measure photons, it also performs the timing measurement and coordinates laser pulses, all from one component. And this substantially reduces the total system cost compared to previous technology based on discrete components in the signal chain and a lot of FPGA processing. Next slide, please. When this cost saving is combined with high performance measurement, we hope that IMX 560 will unlock new applications which were previously too cost constrained for 3D LiDAR, such as intelligent traffic systems, access control, and outdoor automation. And finally, to finish with event-based vision. Thank you. So this is a very exciting technology with us. We think the possibility to realize truly high-speed 3D cameras with affordable off-the-shelf components should unlock new applications. In our lab setup, we are able to measure well over 200 highly accurate point clouds per second at almost 1 megapixel. The speed of 3D measurement this enables could unlock new applications, such as on-arm robotic control and high-speed picking and sorting of 3D objects. We're currently looking for camera partners who'd be interested in developing the technology further. So if that is you, then please do get in touch via our friends at Framos. And I think that's the end of my section, so I will hand over to Flavien.
Thank you, Tom. So my name is Flavien Irigoyen. I am technical imaging expert in Fremos. I'm in charge of optics related topics and as well sensors related topics. So yeah, David, if you could please go to the next slide. So in a quick glance, so sorry, this slide is a little bit dense, but I wanted to give you a broad overview of what the way Fremos can generate some added values to the very insightful presentation and technology from Sony presented by Tom. So in Fremos, we are an official distributor of Sony sensors. So not only for the topics of interest of today, so the event-based sensors and the time of flight, but as well on Swire technology, on rolling shutter, global shutter, and for some other specific large format sensors as an example. So that means that us as a distributor, we are able to provide to our customer some specific sensors documentation made up of data sheets and app notes, but this is not the end of the story. So we have a quite extensive discussion with Sony's technical support team, and so we have the capability through our competence center to understand the customer's application and to proactively ensure some guidance in order to choose correctly and to understand correctly the sensors capabilities depending on the customer's application. So that means that we have a privileged interaction with Sony, and so in the early phase of the project of the customer, we can understand what needs to be anticipated and open up some interesting channel of discussion. In addition to that, we have as well some strong competencies in platform and system. And so we distribute some EVK, so looking to the specific topic, for example, of the event-based sensor, we have a specific Framos sensor module interfaced with a specific board, which allows our customers to have a quick access to the technology in order to evaluate this. So we provide the full hardware and the optics as well in order to generate a proper image, as well as some drivers which are compatible with several platforms, so that you as a customer can quickly use it and experience in a specific application how this technology is working. In addition to that, we have still this privileged interaction with Sony. So in case there are some settings which do not work properly, we have the possibility to replicate the hardware environment with our own modules, with our application engineers in order to understand how to make this up to speed. And finally, as you know, we are optics specialists. So that means that we have a very broad access to some specific suppliers and partners. And so we can, for the future applications, for the future product, after having correctly evaluated the technology, we can correctly propose some optic solution which either can be off the shelf with some of our suppliers, or we can even propose services in order to customize or to do some semi-customization of the optics, since we have a very deep discussions with our suppliers in terms of design and in terms of figure of merit of the optics. So depending on the application, if this is an event-based application or a direct time of flight application, which requires, for example, the optics to work on some specific environment and some specific sensitivity to some laser information. That means that there are a few things to take into consideration for the optics to be performant. And that's it for my part.
All right. Thank you very much, Flavien. Thank you very much, Tom, for the great presentations. That was really nice to have a look at. I would like to ask the both of you to turn on your videos again, and we are directly starting into the Q&A session. We've got about 3 minutes left on the clock, and there's many questions piling up, so I would suggest we start right into it. So first question, I think, goes in direction of you, Tom. This is about the IMX560 launch and sample availability. So there's kind of two questions in it. The one, when is it available, and how to get samples, and also whether there's an MOQ attached to getting samples.
Thank you. Yeah, thank you for the question. The good news, it has launched officially. So if you go on the Sony Semiconductor website, you'll be able to find some information about IMX560. Samples are available in very small quantities. So if anyone would like to evaluate the documentation for IMX560 and then potentially order samples, then please get in touch with our friends at Framos, and then we can facilitate that.
All right. Thank you very much, Tom. Next one is a bit more technical. I'll leave it up to you who wants to take it. About the IMX560. Question is if it's needed to trigger the sensor while the emitter and laser starts emitting. So in principle, how does the measurement of time of flight work with the 560?
Maybe I can tackle that one. So IMX560 can generate the trigger pulses for the laser itself. So that means that the timing is all consistent. Essentially, I think one of the big strengths is a lot of basically the high frequency electronics that you would need in the ToF system are integrated within the chip. So yeah, it does more than just measure. It also can generate the pulse train you need for the measurement.
All right, perfect. Thanks a lot, Tom. Last question we can take now in this time, and the rest would be answered later on. Again, it's a technical one, and again about the 560, and this is about the measurement accuracy. So you mentioned before about the benefits for the different ranges, and now question is the measurement accuracy of the 560 better or equal compared to indirect time of flight sensors?
I guess, would you like to take this one,
Yeah.
Flavien, or?
Would you like to take it on?
Maybe I can take this one, and probably you can as well add some of your viewpoints, Tom. So depending on the situation, direct time of flight, let's say, has the advantage of ToF to give a constant, let's say, rather constant accuracy of measurement, of distance error measurements along a quite long distance. So that means that for very short distance, as illustrated by the slide of Tom in the beginning of this presentation, ToF might be a better suited technology for really short distance because the precision and the accuracy might be better. But if you go to longer distance, the advantage of the direct time of flight is clearly on the histogram reconstruction of the signal, and then you are less dependent on some, let's say, physical phenomenon which can happen on longer distance, like multiple paths occurring on the back reflections, and as well bad quality of the optics. So the system is more stable.
Right, perfect. Thanks a lot, Flavia, for the insights. With that, I'd like to wrap up the Q&A session. As mentioned, any remaining questions, feel free to hand them in at any time. The ones that are already posted in the chat, we will be taking care of and come back to you afterwards. With that, I'd like to thank again the speakers, Tom and Flavia, for the great presentations, and also thanks to the audience for your attention. Just a quick reminder, please keep in mind that there's a couple of webinars piling up and coming up, as you can see here, July 3rd, 10th, and 24th. And if you would like to contact Framers in the meantime, please scan the QR code and fill out the contact form. I'm happy to discuss further with you. Thanks a lot, everyone. And with that, I'd like to wrap things up and close the webinar for today. Bye-bye.
Thank you, everybody. Bye-bye.